Se ve, Alejandro, se ve.
Thank you, madam. Hi, Libby. Can you confirm that you can see us?
Yes.
Hi, Libby. Do you hear me?
I can hear you.
Yes.
Okay. 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 All the team can hear me?
Yes, I can.
Okay. Let's start. Good afternoon, everyone. We are Team 104. I am team leader, Alejandro Pineda, of Autonomous University of Baja California. Our project is Cimarron. We are going to 10K cuts, and now we are going to present. Next, with Miley.
Yes, who are we? We are a university club from the Autonomous University of Baja California, Mexico. Our foundation started in 2019 by 8 aerospace engineering students. We are a multidisciplinary group of students who are looking to promote and develop technologies for space in our country. We strive to promote interest in science and technology within and beyond on institutions due to the value they bring to people's life and the progress of Mexico. Next slide, please. Mm. Oh, no. Demographic data. Yes, the Club for the Research and Development of Space Systems, CIOTSE, has active from 3 out on the 7 municipalities of the state of Baja California, Tijuana, Mexicali, and San Quintin. Next slide, please. And yes, we have worked hand in hand with our sponsor as Jaco, GKNA Aerospace, Itzela, Tu Diseño, Sony's Car Wash Vacuums, OnShape, and our university. Thank you.
Now I'm going to talk about team composition. First, team leader, followed by sub-leader, Miley. Our team is composed by three principal divisions: rocket main integrity, rocket recovery and communications, and simulations and payload. Each one has three areas: propulsion system, aerostructure system, airbag system. By recovery communications, we have recovery system, airbag system, and ground station system. Finally, rocket and payload have payload system and simulations division. Each one have their own subdivision. Yes. Next slide, please. Okay. There is some general data about our rocket, like the apogee, length, diameter, motor, mass without motor, length of mass, maximum speed, radial exit velocity, center of gravity, center of pressure, and average stability. This is the left of stability. I made a mistake. If you have some question, Jimmy, you can tell me at any moment. Okay. Next, please. Well, we have the main rocket composition. First, we start with an Osman aluminum tip, followed by nose cone, the payload, the upper airframe, the airbrake system, the avionics bay, the middle airframe, lower airframe, our composition of configuration, the fins, and finally the bulkhead. Next, please. Now we are next with the nose cone.
Good afternoon. My name is Anna, and I'm nose cone leader. Next slide, please. Okay, so some general specifications of the nose cone. Our rocket's nose cone has two functions. The first function is to serve as an aerodynamic enclosure that holds the air during the forward motion. Its secondary function is to serve as a compartment for the payload, protecting and storing the payload. Its mission is to endure aerodynamic forces during flight, and its type is LD hack requirement. Next slide, please. The nose cone has 6 components, starting with the tip, which is aluminum 6061T6 and has an M3644 threading. Then in the inside, we have tip coupler, which is also aluminum 6061T6 and has in the interior a M3644 thread. Then we continue with the nose cone structure, which is a composite lamination of carbon fiber and fiberglass. Then we continue with the shoulder, which is exclusively fiberglass. Then we proceed with the bull plate, which is aluminum 6061T6 and is half an inch. We use 6 M4 4.7 fasteners, and then finally we have the half an inch eye plate. Next slide, please. For the dimensions, we have a nose cone length of 25.5 inches and a shoulder length of 10 inches. However, out of those 10 inches, 1.5 inches of the shoulder length goes inside of the nose cone. In total, we have a 34 inches length. The shoulder caliber is 1.96. Next slide, please. Finally, for the manufacturing process of the nose cone structure, we use a 3-axis CNC machine in order to create a mold with fine wood. And once we had the mold, we proceeded with the construction of the structure using the head layout method and performing a vacuum process. Once we obtain both parts of the nose cone structure, we use a GD weld epoxy to join the parts, and finally we use 1 layer of fiberglass to finally join both parts. For the nose cone area, this will be it. Thank you.
Okay, hi, good afternoon. My name is Leonardo. I am the leader of the iframes. I will telling you the important aspect of for each one. Our rocket is made up of the upper, middle, and the lower iframes. The next 3 iframes have same measurements: 5.12 inches outer diameter, 4.92 inches inner diameter, 0.098 inches thickness. In a moment, I will mention the length and the weight of the iframes. I start with the upper iframes. Count at 37 inches length and approximately 3.84 weight pounds. X-Force 7781-50 woven fiberglass fabric is used to manufacture the upper part of the iframes. This fiber was chosen due to the need to not interfere with the avionics communication with the ground station during flight, as carbon fiber would do. We choose to use polyester resin with a proportion of 1% catalyst for the top of the our structure. The manufacturing technique of this component is hand layout. Next slide, please. The second iframe is the middle, bound at 34.25 inches length and approximately 3.55 weight pounds. Carbon fiber filament and epoxy resin were used to do their excellent mechanical properties. Okay, next slide, please. On this occasion, we decided to implement a new manufacturing method, and this method is called filament winding. Filament winding is a manufacturing technique for creating composite material structure. The process consists in a winding tensioned filament impregnated with a resin in a cylindrical mold. This new manufacturing method we use to make both the middle iframe and the lower iframes. Okay, next slide, please. To finish, count at 39.37 inches length and approximately 4.085 weight pounds. The lower iframe was manufactured by filament winding technique using the carbon fiber and epoxy resin with a proportion of 30% catalyst. In another hand, we use two large Darling 1515 rail buttons. One is located in the middle of the iframes, where the center of gravity is located. And the second is located in the lower iframe, between the fin and the butt tail. These rails will allow the rocket to be inserted into the base launch. These two rails are in different iframes to ensure that they are centered on the launch and base, and we will use the mark on the two iframes. Okay.
Okay, so next up we got payload. If you could help me with the next slide, please. Okay, here we're gonna talk about the mission objective in an overall manner. We see our project as a feat of modern biotechnology by carrying an herbaceous plant in the payload of the rocket, withstanding extreme temperatures, isolation forces, and the microgravity of space. Our intelligent capsule ensures the survival of the crowd throughout its journey, with three phases or system controls all vital aspects from nutrient supply to adaptation to the space environment and real-time monitoring. The electronic control system ensures that our crop is always in optimal condition, even in the most hostile environments. Next slide.
Okay. The payload is composed of multiple subsystems which fulfill a specific function, but together allow the optimal operation of the automated aeroplane system. I will mention below a general description of each of subsystem presenting the payload. The sprinkler systems, this subsystem is necessary, has the necessary parts for the operation of the aeroponic system and is made on the following parts. Water tank, this will made with resin and drain plate. The material of the from the for the parts is indicated on the right side of the name. In this case, of drain plate, is as is in the material is abbreviation for the stainless steel. And the next part, oh no. Okay. The next part is the sprinkler flower, and the other subsystems is the electronic bay. This space will contain the electronic system necessary for the optimal functioning of the aeroponic system and switch and microcontroller batteries or sensors. The supports and retainers. The system has a simple and crucial function on the payload as the char in is in charge of the providing support and the permanent union with internal wars to the NOSCOM, thus the interest moments. Um, an important fact in the most of the parts is that make up the federal manufacturing by 3D print. Next slide. Um, the growing method. An aerophonic system works by suspending on the rods of the plants in the air and periodic spraying with the fine mist of nutrient solution, taking care of the specific needs, the monitoring and attention of the optimal plant growth. And the basic structure is the rods is suspended in the dark enclosed space to the plant exposed to light and air. And the next is the nutrient spraying. Mix of the rods with nutrient solution regular intervals to keep rods moist and oxygenate. The parameter controls of the growth method is temperature, pH, humidity, oxygenation, illumination, and sensor of the monitoring and the adjustment controllers to make the optimal range of the cultivars lamps. And the fusion of the sprinklers is of X-vane nozzle, and the X-vane nozzles use vanes to produce high speed rotation on the pressure the liquid flow inside the turbulent chamber. Liquids are atomized by the centrifugal force that produces a solid steam jet with a full cone spray pattern. Next slide.
Hi. For the plant, we choose the microgreens. Microgreens are young sprouts and of vegetable plants and herbs like radish and lettuce, broccoli, and it contains a lot of nutrients and vitamins and amino acids, and it helps to cleanse the body. For advantage, the microgreens can be eaten completely, so we don't have to be worried about the residues in the space. The growth timeline is shorter than other plants. It took like 7 or 15 days to grow, and it consumes the minimum of water, and it won't need fertilizer, so you haven't to take care for this part, and it's perfect for small places. As we can see, the system is really small, so we want to grow plants who contains a lot of nutrients and vitamins in small places, so this is perfect for us. And for these disadvantages, it requires time and constant attentions. Um, for the tensions, we have to oh my we have to supervise the pH and the nutrients in the water solution.
Okay. Here we have our avionics blade. It's composed by a coupler and a band of airframe. the both plates, the lower and the upper. Here is the recovery ejection system, the CD3 system. As you can see, there is here is a manufacturer inside. It's composed by fiberglass of the avionics plate with polyester resin. The internal diameter is 4.92. And next slide. Okay, so here is the dimensions of the fiberglass, the van, and the bolt plates. The coupler, the avionics plate, has 1.3 the length of the dimensions required by ESRA. 1.3 times the diameter of the rocket. That means we can accomplish that length required by ESRA. Next slide, please. Okay, and next with lower airframe.
Hi. Now we are going to present the lower fuselage. First, is the coupler, the lower coupler. Here is a lower coupler. It was made of fiberglass, hex force, and 77, 81 fiberglass, and the respective length of the coupler are 6.1 inches. It means is 1.2 times the diameter of the lower fuselage. Yes. And we glue them with JB weld in this part. Now we have the fins. The profile is a delta 5. And the fin flutter is 2,105 feet per second. And next, please. Yeah, the manufacturer, it was a hand layup with vacuum pressure, and the cutting of the fins, it was in a CNC machine. We use epoxy, JB weld epoxy, to attach them to the fuselage, and we use the tip-to-tip method to join and connect the fins to the lower fuselage. We use layers of fiberglass and one final layer of carbon fiber. As you can see in the image, we use the 3D printed aligner to align the fins. And then next is we have the motor tube. We buy it in warehouse. The material is fiberglass, and as you can see in the slide, we have the outer diameter, the of 5.1 inches. The inner diameter 4.9, the thickness 0.098, and the length of 39.37 inches. And the center rings, it's the material is multidirectional fiberglass. And the next piece. Finally, we have the motor retainer and the bolt tail. And the motor retainer and the motor retainer, it's a minimum diameter motor. We glue them with JB Weld epoxy, the red one. And I see, yes. And then we have the bolt tail. Finally, here is the bolt tail. It's machine. It was machined in aluminum 6061, and we attach with four fasteners. Or one car. What?
Hello, my name is Cesar, and I am leader propulsion. Okay, next slide, please. Okay, the propulsion system we have chosen is an Aerotech M2 500 PS RMS 98/10-240 CUTS rocket engine. We chose this motor because it has the thrust and speed needed to lift a rocket to 11,000 to 156 feet, which means an 11.2% of extra altitude in order to have a tolerance for the air brakes applications. Okay, the motor hardware consists of retaining nozzle, casing, retaining forward closer, and forward closer. And the function is produce the thrust by the explosion of gases at high pressure and give movement to the rocket. And this motor use blue thunder propellant. And next slide, please. This motor is consists of casing specifications and propellant specifications. The model is RMS 98/10-40. The length is 27.94 inches. External diameter is 3.87 inches, and weight is 5.4 pounds. The propellant specifications is the initial thrust is 2,577.9 newtons. The total impulse is 9,671.0 Newton seconds. The max thrust is 3,710.9 newtons. The ISP is 209 seconds. The burn time is 3.9 seconds, and the propellant is a Blue Thunder. Next slide, please. And this the thrust curve graphic. In the vertical line, show the thrust in newtons, and the horizontal line show the time in seconds. And that's it.
Hi, my name is Ian Quiñones, and I'm the avionics lead for this mission. The Simrone Avionics underscores our commitment to reliability and innovation, integrating two commercial flight computers and two student research and developed flight computers. I would like to kick off with the commercial flight computers. For this mission, the main altimeter chose carefully was the Altus Metrum AC Mini, which is a dual deployment altimeter, has a 9-volt alkaline battery to power its components, and it comes in handy with its mini USB function for retrieving information afterwards in the mission. For redundancy and security, we chose also the MissileWorks RRC2, which is also a dual deployment altimeter, has the really important feature of power shortage protection, and is also powered by a 9-volt alkaline battery. Sorry. For our switches, evidently, we need a way to power on and off our components, both for safety and power maximization. That's why we chose the small Omron SS5GL relay switches, an arrangement of 4 switches that will form a larger pin type switch. It's important to notice that these altimeters are all set to deployment in apogee and 1,250 foot above ground level. Next slide, please. Furthermore, this year we developed two multifunction flight computers that will accomplish both altimeters and navigation tasks. SRAD-A being the main computer with the most features, is a dual deployment altimeter, has air brake control authority, GPS, orientation, and acceleration data collection and transmission via long range 915 megahertz. It's powered by two 9-volt alkaline batteries, one powering the microcontroller and the other one powering the E-match power. SRAD-B, it's a mirror of the SRAD-A, and it just has the removal with for the altimeter and air brake authority functions. It's also GPS, orientation and acceleration collector, and transmitter with long range 915 megahertz data. It's also powered by a single 9-volt alkaline battery, and it's important to note that SRAD-A altimeter function, it's also set to apogee and 1,250 foot above ground level. Next slide, please. Here we have the wiring diagram for the Cimarron avionics, where we can appreciate the connection between components assisted by color symbology. For example, red lines or red cables stands for positive connections, black stands for ground or neutral conductors, the yellow one stands for signal connections, and the purple dotted lines for wireless connection. There are also boxes that we can see. Blue stands for the SRAD flight computers, yellow for the COTS altimeters, green, which in this case, there will all be 9-volt alkaline batteries, it's the power source, orange will be switches, and red for E-matches. Next slide, please. Finally, but not least, this slide shows isometric views of the several fixtures for our avionics components. They're all 3D printed in PETG, which has a melting point of 150 Fahrenheit, ideal for desert operations. These fixtures are named by their position in the avionics bay correspondingly, level 1 being at the bottom and level 3 being at the top. Level 1 houses the COTS altimeters and two 9-volt alkaline batteries. Level 2 is essentially our pin switch, which houses the 4 Omron SS5GL switches mentioned before. And level 3 houses the SRAD flight computers and three 9-volt alkaline batteries at the top. It's important to mention that all these fixtures are fixed in the avionics bay via 4 nuts of 3/8, both at the bottom of the plate and at the top of the plate. That will wrap up the avionics for the Cimarron motor rocket.
Hello, good afternoon. I'm Andrea, and I'll introduce you to the ground station area. Okay, first we have our goal, and is to design a system to monitor the mission status of our rocket. And to achieve this, we need a highly reliable ground station system that maintains the communication link so we can continue with our mission. On the right, you can see a diagram of that data received at the ground station from the rocket. This includes information from the avionics flight computers as well as payload. And here we see a diagram of the components used in the ground station. We have an external antenna that offers higher signal gain connected to a single board that contains a LoRa module, which is connected via micro USB to the ground station computer. Additionally, we have a power bank to ensure power supply to our computer during our mission. And for data reception, we use the LilyGo T-Beam. This is a commercial single board with an ESP32 microcontroller and an integrated LoRa module. This helps us to maintain a functional and reliable system, reducing potential points of failure compared to using individual components. And the data is received via LoRa at the 915 megahertz of frequency. And the data to receive from the rocket includes GPS, altitude, gyro, acceleration, temperature, pressure, real altitude. And yes, as I mentioned before, we use an external antenna for higher signal gain. And we have a graphic interface. This graphic interface was made in LabVIEW, and we chose LabVIEW for its user-friendly visualization system. A key feature of this interface is that it includes an input text box, which displays the data in a concatenated string. And we have point values that shows latitude, longitude, and number of detected satellites. We have also a graph. We have like plotted values that shows data from the accelerometer, gyroscope, barometer, temperature, altitude, and so on. So with this, we ensure easy interpretation of all the data received. This allows us to quick understand the data received. And we also have the option to save all the data to a selected text file. And this is for the ground station. Thank you.
Hi, I'm Jared Ortiz, recovery leader, and now I'm going to talk about the recovery system. Okay, first, parachutes. The parachutes that we are going to use in the competition are homemade, with Rayson nylon fabric and paracord for the ropes. About the characteristics of the parachutes, the drop parachute has a diameter of 36 inches, a descent speed of 68.75 feet per second. His deployment is at apogee, and the parachute is green. The main parachute has a diameter of 86 inches, a descent rate of 20.08 feet per second. Its deployment is planned at 1,250 feet, and the color of the parachute is red. Both parachutes have a spill hole to increase the stability of the descent. The spill hole that we made has a 50% radio to the diameter of each parachute. Also, the parachutes will be protected by a 9 inches Nomex fabric during the flight of the rocket. In the slide, we can see the main parachute. And next, please. Okay, now talking about the deployment system, CO2 system cartridge will be used, activated by a C3 system. For primary and redundant charge, 25 grams of CO2 are being used. In total, 4 CO2 cartridge will be used during the flight. The CD3 system is triggered by an image, which activates a small share of black powder. The black powder pushes a piston inside the CD3, which perforates the CO2 tank. We design and machine the CD3s by reverse engineering the Rush text model. And in that picture, we can see the bull plate with the CD3s and the CO2 tanks. Next slide, please. Now, the chokers. The chokers that we're going to use in the competition are half-inch tubular Kevlar, which have a resistance of 6,000 pounds force. In the picture on the right, we can see a diagram that shows the harness's length and a representation of the rocket descents. We can see the choker A is 24 feet long, and the A1 side connects from the nose cone to the drop parachute, while the A2 side connects from the drop parachute to the upper fuselage. In the choker B, the choker B is 36 feet long, and the B1 side connects from the avionics bay to the main parachute, while the B2 side connects from the main parachute to the middle lower fuselage. Now, talking about the mechanical links, we are going to use 3 8-inch steel quick links, which have a load limit of 2,645 pounds force, while U-bolts and E-bolts are used in the fuselage. The parachutes use a steel A swivel in their connections. Next slide, please. Now, here we can see the flight profile graphic of the Cimarron, showing the phases with estimated times. The phase 1 is the pre-launch, where the necessary operations for the launch are performed. The phase 2 is the power flight, where the rocket reaches a maximum speed of 878 feet per second. The phase 3 is the ascent, when the engine exhausts its propellant and ascends during seconds 4 to 26. The next slide. No, back. Well, can you come back? Okay, yeah. And phase 4 is when the rocket reaches the apogee with a simulated altitude of 11,256 feet, and the first recovery system is deployed here, the drop parachute. The phase 5 is when the drop parachute descends, where the drop parachute will descend at a rate of 68.75 feet per second. The phase 6 is when the rocket descends to an altitude of 1,250 feet, and the second recovery system, the main parachute, is deployed. At the moment, the speed of descent must be 20.08 feet per second. And now, in the last phase, is the rocket descends to the ground, and we can do the rocket recovery. Now, to finish, I'm going to talk about the shirt pins. We are going to use nylon shirt pins 440 with a length of half of inch to hold the fuselage together. It is planned to use 3 shirt pins for fuselage joint. And the bend holes, 4 bend holes with a diameter of 1/4 inch will be used, 2 in the upper fuselage and 2 in the middle fuselage.
Good afternoon. I'm Sebastian. I'm air brakes area leader. And to start, the function of the air brake system is to generate drag, so we get closer to the goal of 10,000 feet above ground level. And so this next one. Well, the maximum angle of opening of the air brakes is 40 degrees. And it generates a drag coefficient of 2.2 and generates drag force of 1300 newtons to 27 newtons as the max speed numbers slow down. The brake system opens at an altitude of 65% of the flight path at an altitude of 6,500 feet. And so using this brake system, we're trying to get an apogee of 10,597 feet. Okay, the parts of the air brake are made. These are the flaps, which are made of carbon fiber, and the core is made of fiberglass. And the mechanism is a joint of push and pull and pin slots movement system. The mechanical parts are made of aluminum, 7075. And to cover the slots where the brakes are placed on the control band, we use some rubber coatings. And also the brake system goes attached to the avionics bay using the same three rods as the avionics base structure is attached to.
Hi, I am Dalia and I am the simulations lead for this mission. Well, please. As you can see, the rocket was designed using OpenRocket, Rasa Hero, and RocketPy, where simulations were conducted. Subsequently, all the obtained results were collected, including data on the rocket performance, such as maximum velocity reached, maximum altitude reached, total flight time, flight stability, and other relevant parameters. After gathering all the results from the simulations in OpenRocket, Rasa Hero, and RocketPy, a detailed analysis of these results was carried out. This analysis focused on evaluating the rocket performance in different key aspects, such as maximum velocity reached, maximum altitude reached, total flight time, flight stability, and additionally, the other relevant parameters that could influence the overall performance of the rocket, such as motor efficiency, aerodynamic resistance, and structural stability, were examined. The main objective of this results analysis was to identify areas for improvement in the rocket's design and simulate flight parameters. This analysis enabled informed decisions to be made to optimize the rocket design and maximize its efficiency and performance during flight, mainly. The next slide, please. Okay, to achieve maximum redundancy and simulation with integrated air brakes, it is necessary to use the Python library called RocketPy, which specializes in high precision simulations up to the apogee. To conduct the simulations, various parameters needed to be added. These parameters include launch conditions, the type of engine to be used, and the structural specifications of the rocket. The purpose of including these details is to ensure that the program takes into account each component of the rocket, enabling us to obtain more accurate and realistic results. Next slide, please. Okay, as you can see, the following table shows the drag coefficients obtained during ANSYS fluent based on the Mach number per opening angle of the A brakes. A previously calculated maximum opening angle of the 42 degrees is used, and the air brakes are deployed when the rocket exceeds the 6,500 feet. Additionally, you can see the different pressure and velocity contours obtained directly from the ANSYS program, where you can appreciate the different angles applied to obtain the parameters needed to complete the rocket pi simulations. Next slide, please. Okay, continuing with the obtained results, a comparative table was prepared, clearly showing how the use of A-brakes allows us reaching an altitude much closer to the target of 10 key feet. Comparing the results with those obtained without the application of air-brakes, a significant improvement in the control and precisions of the attained altitude can be observed. This comparison allows to conclude that A-brakes effectively fulfill their function of adjusting the rocket trajectory and velocity, crucially contributing to a successful mission. Moreover, these results underscore the importance of A-brakes in optimizing rocket performance and achieving set objectives. Okay, in the subsequent images, it is possible to observe the 3D flight trajectory of rocket pi in the figure 1 and the 3D flight trajectory in the vertical launchpad area on Google Earth in the figure 2, both obtained from rocket pi simulations. These visualizations are essential for understanding and predicting the rocket trajectory, precisely identifying its landing location, and evaluating possible deviations from the planned trajectory. And well, with this conclude this presentation. Thank you for your time and for your attention. Please feel free to ask any question or seek further clarification on any points discussed. Thank you.
Okay. Is it Q&A time? Hello, can anybody hear me?
Hi, Jimmy.
Oh,
yes, we can
Yes.
hear you. Okay, do you have any questions about
Yes, but
any area?
but first a statement. That's a wonderful presentation. I want to thank every one of you for being willing to get up and present, especially in English, what might not be your natural preference. But thanks for doing this old guy a favor and telling me about your rocket. The project is beautiful. The rocket is beautiful. It looks really good. I have very little to say about it other than how great it is. I'm proud of you for being willing to build that and bring it to New Mexico where we launch it and I get to watch it. This is fun.
Thank you so much for your comments, Jimmy.
Yeah.
Thank you very
But
much.
a great hard work during.
We really appreciate it.
I'm sure it's been a lot of work and you've done very well at it.
Thank you.
Do you have a couple of questions?
Okay.
Well, one is that the final color of your rocket, or is it going to be painted a different color before you take it to the launch?
Yes, we are going to paint it before the competition. Just
Okay.
we are making the last configurations and hands-on working. Just we need 2 weeks more in order to paint it.
Excellent. What color will it be?
The color selected by the team is red.
Okay, that's not too bad. Highly visible for one thing. And what I'm getting at is some of your components are made out of 3D printed material. And I know you're using PETG, but it is still subject to heat. And I've seen PETG parts melt in the desert. What happens is the rocket will be sitting on the pad sometimes for an hour, sometimes more in the sun. And the rocket acts as a little solar collector, and the heat can go way up inside that rocket. So I would suggest a couple of things. One is to do some tests, to take a version of of something you've made, seal it up like a rocket would be in the same kind of material if at all possible, and set it in the sun in Tijuana or wherever you're at, and let the Mexico sun bake it a little while and see how well it holds up. Now, you may have already done that.
Can you repeat it again?
Okay.
Please.
I suggest do a test to see if your PETG products will hold up under real life circumstances.
Okay, we are going to make it. We are going to Laguna Salada in 3 weeks in order to launch a rocket model. Not the Sigma run, but we are going to make a launch of a model rocket with the CD3 system and the telemetry by the avionics. And yes, we are going to use the PETG, and we are going to see how is the systems, how works the systems. How works the systems.
Okay, good.
The weather here is the same like Las Cruces, but it is more warm, dry and dry. We get like 50 Celsius degrees here in Mexicali by that dates. So it is too close, even higher than Las Cruces.
Good. Then you should have a good environment for testing.
Yes. Here is our finally rocket design.
Oh, that's beautiful. Yes. Who designed that?
Yes, the marketing team.
Good. I like it.
Okay.
Okay, I have another suggestion. And this has to do with your checklists. And when I looked through them, I saw a glaring omission. I don't see any checklist about what you should do at the pad when you're setting up your rocket. And that's one of the most critical checklists. And if you don't have one, they're not going to let you fly.
Yes, that's correct. We didn't add it at the moment of the upload of the technical report, but we are working. We are working on it.
Okay, good.
As we haven't finished the rocket yet, and we want to make a really nice checklist about the launchpad moment.
Oh, good. I was just wanting to make sure that was in your plans.
Yes, it is.
Okay, and that's about all the comments I have. Any question for me or?
I don't know if some team member wants to ask something. I have to mention that we are 50-50 members team. in 2 cities. The first 50 is in Mexicali and the other in Tijuana.
Oh, excellent.
That's why the rest of the team is is online.
Oh, interesting.
Yes.
Oh.
I don't know if you want to see more close of rocket. We got time if you want.
Well, you've shown me the parts, and I think that's the important look because they all look to me well made, well built, well designed.
Okay, thank you.
I'm okay with that.
Okay. I made a mistake. Sorry.
Okay.
I hear that you want to see the rocket again.
Oh, yes, of course I do. But I really want to see it fly. Not this minute. You don't have to fly it now. Just in a few weeks.
Okay. But in 1 month, 1 month left.
Yeah.
Okay.
So if you don't have any more questions for us, we will. We want to say thank you for your time, for listening to us, for taking the time to review our technical report, and for your recommendations. We are very proud of our work, and we hope to see you soon in Las Cruces, Nuevo Mexico.
Yes.
Thank you.
Well, you should know I love my job, and you're the reason why. So I thank you.
No, thank you.
Thank you too, Yumi.
Yeah.
So,
Alrighty. I'll write a report on this, and I'll send you a copy. So you'll be hearing from me at least one more time.
yeah.
But do feel free to write if you have any questions or concerns. I'll be glad to help any way I can.
Thank you. Thank you so much.
Thank
We
you.
really appreciate that.
Alrighty. The bye-bye time?
Yeah.
Oh, here. You can say bye-bye to Florida for the moment.
See you.
Warm and wet here.
That's cool. I like the remaining time.
Alrighty. Bye-bye.
Bye.
Bye. Bye.
Bye.
Thank you.
Bye. Thank you for your time.
Wow.
Oh,
Épico.
bravo, bravo.
A pesar de las dificultades, quedó excelente.
Sí, sí.
Ya saben, equipo. A ver. Chismecito.
Siguiente.
Miren, se nos fue la luz, por eso.
¿No sigues trabajando para esto?
Es que lo suben a YouTube.